Hi, my name is Ewan. I'll be covering lab for oscillations. The purpose of the lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring, and construct a computational model that predicts the motion of the spring mass system, then compare the predicted and observed data. My results were that the predicted and observed data differed slightly due to human error/assumptions, but ultimately were very similar, and also that the change in total energy of the system was zero. Here are some of the fundamental principles, formulas, and assumptions in this lab. First is Newton's second law. We are predicting motion, which means we include the velocity update formula, position update formula, and momentum principle. Next is the energy principle. We find that the change in total system energy is equal to the change in kinetic energy plus the change in spring potential energy plus the change in gravitational potential energy, which is equal to zero. This is because the system is assumed to be Earth, mass, and the spring, meaning no work should be done on the system. Kinetic energy is equal to 1/2 mv squared, spring potential is equal to 1/2 ks squared, and gravitational potential is equal to mgy. Finally, our forces are spring force and gravitational force. We assume there are no other forces present. Spring force is equal to negative ks times s times l hat, and gravitational force is equal to mg. Now moving on to the model code. We're getting the mass as 0.402 kilograms. I found the initial position and initial velocity using the tracker data. Lines 56 to 63 describe how the code visualizes motion measurements. And finally, the time is equal to 0 initially, and the delta time was also given. Continuing on, we have constants and energies. We found that G is equal to 9.8, Ks is equal to 5.95. To find this, you have to find the period of oscillation, as seen in the bottom right. Ks is equal to 4 pi squared times m over the period of oscillation squared. Next, we found the relaxed length of the spring, L0. And that is equal to 0.0377. We found that because L was given as 0.7 meters, and L minus mg over k gives the relaxed length of the spring. Next, we had to specify the vector L. L is equal to the position of the ball minus the position of the spring. The direction of L hat, is equal to the vector L divided by the magnitude of L. And S is equal to the magnitude of L minus L0. And now we have the energies. Kinetic energy is equal to 1/2 times the mass of the ball times the magnitude of the velocity squared. Gravitational potential energy is equal to the mass of the ball times g times the y position. Spring potential energy is equal to 1/2 times ks times s squared. And the total energy is the sum of all its components. The loop code is for the duration of the tracker data, which was 9.5 seconds. First, I defined the initial energies, then I defined the forces in the system. Force gravity is equal to the vector negative mg in the y direction. The spring force is equal to negative ks times s times l hat, and the net force is the sum of those two. Next, we have the velocity and position update formulas, as derived from Newton's second law. Then we have specifying the vector L again, which is exactly the same as specified before. The energies are also defined exactly as before, except now we calculate the change in energy, which is itself minus its initial. The graph output of the code color codes all the energies as follows. Kinetic energy is blue, gravitational potential energy is red, spring potential energy is green, and the total energy is orange. Here are the results. In the change in energy versus time graph, the delta E always remains 0, because the sum of its components always equal out to 0. The x position and y position versus time graphs compare the model and experimental data. The data is roughly similar, which can be attributed to human error and assumptions on forces acting on the system. Lastly, we have the what does it mean questions. The first being, for your model system, is the energy principle satisfied? I said yes. The system includes the Earth, mass, and spring, meaning no work should have been done on the system, which is supported by the fact that the change in total energy was 0 throughout the model. The last question is to compare the estimates of the period of oscillation for the x position data and the y position data. I found that the period of oscillation for the x data was 1.64 seconds, while the period of oscillation for the y was 1.51 seconds. The period of oscillation for the x was almost exactly equivalent to the overall period of oscillation I found before. But the period of oscillation y has a more significant difference, which I assume is due to the fact that the forces in the system are mostly in the y component. And that should be it. Thank you for sticking through this.